let's just get to it. All right, so I didn't ask you guys about extension 1, so I know where you're kind of struggling with extension 2. Have you guys already mapped out what you're struggling with in extension 1, or do you want to do that first? Okay, because that's always like a good starting point. So extension 1. Now, topics. All right. So how did you guys, I'll start here because I want you guys to be very brutal. Like, okay, look, I'm very easy. Like, I don't get butthurt or upset very easily. That's how you get good at teaching. You just don't care. Like, so if you tell me, the last lesson was a complete waste of time, I'm cool with that. But I just want you to be very honest with me. What did you find helpful or not so helpful about the last lesson so I can like tailor to you what you need, like what you need for the last bit? What do you guys feel like you'll need? Did you find it helpful, not helpful, interesting, not interesting? What are we dealing with?
It was helpful.
Yep.
I think that like I understood complex numbers a lot more.
Yep.
After that.
Yep. Okay.
Or maybe just like a bit too much time on explaining it all.
Yeah. Right. Because that's generally what I do. I generally spend too long. A common criticism I get a lot of the time is that I spend too long sort of explaining the concept and not enough time doing examples. That's why I like to ask you guys 4 examples prior to class on the stuff you struggle with. So every week from now till the HC, I'd like you guys sort of like, I'm assuming you're going to be doing papers. I'd hope so. And so when you get struggle questions, what I like a lot of the time is, even if you can do the question, sometimes seeing a different way helps a lot. Right, so if you're doing a question, you're like, this is unreasonably difficult, surely there's an easy way. I promise you there's an easier way. You know what I'm saying? So if you're doing a problem and you're going, okay, I can kind of get it right, but I don't know what I'm doing wrong or how I could do this better, those are usually the questions where you got the most bang for your buck improvement-wise. I'll close the door because I'll let it like heat up a little bit. And let's just do this. So let's map out where you guys need to focus and then we'll go from there, shall we? So the topics are, so we have trig. Trigonometry. So your name is Lauren, right? Yeah, okay, cool. Trigonometry, we've got vectors. We've got binomial, which I can help a lot with, by the way. Perms and coms. And am I missing one? Integration. Differential equations. Anything else that I'm missing? Yeah, the basically the only proofs that you really need to do here are induction, so I'm just going to put induction here. Do you guys feel like you get induction? Like, do you understand what you're doing, or do you just kind of like do it? Because that's always a question I ask people. I think back in the day, like, so just sort of a bit of context here, I spend a lot of time obviously getting to the root of like why things work the way they work. Julian's a lot more like how to do. He's a lot more on the how and I'm a lot more on the why. Is that fair? So for what we kind of do a lot of times, like I try to sort of really give you a deep understanding of why something is happening, and then I kind of leave the how to you, because a lot of the time like just doing practice is quite easy, and then figuring out where you're getting stuck. And when you're getting stuck, you're always getting stuck because there's something you don't understand. That's kind of my thesis, and obviously my marks don't lie that it works. So like they're very, very high, as long as you are sort of in this loop with me where you're like, okay, getting stuck, telling me where you're stuck, and then I can get you unstuck, and then we just keep in that loop. Pretty much by the end of the HC, I was telling Lauren that from now to the HC, this is pretty much where I see the most improvement historically, right? So if I was to sort of graph it for you, to be like being completely honest, let's say this is HC mark, and this is time, year 11, year 12, and this is trials right here, right? If I was to graph for you if you took the HSC today, what your mark would be, right? It would kind of obviously start close to 0. And then by the time you're at the trials, it kind of looks a little bit like this. And then people will get completely screwed by the trials. The average mark of the trials historically has been a fail, right? Not with my students that I've had from year 10, but across the board, the average mark is usually a fail, okay? Then this happens. Okay, so what we want to do is we want to really get that inflection to go as high as we possibly can. So in order to do that, I'm going to need you to be very brutal with me, because we only have a very short time to get to know each other. I've seen some miracles happen from now to the HC though. I have literally seen students go from like a band 4 to a band 6 many times. Make sense? So what I will need you to do is be very brutal with how I'm teaching you. Just be like, this isn't working for me. Just be like, okay, cool. Let's iterate. Cool. So I want it to be like a partnership between you and I. If you think that what I'm doing is not helping you, just say it. I'm not going to get upset at you or anything like that, right? I know that's hard to say because a lot of the time we have this bias where it's like I feel bad telling people that they suck. You know, that's kind of one of those things. So I don't care. I just want you to do as well as possible. Like, don't worry, my ego's not going to get hurt, okay? But what I do need you to do, so to be very brutal with me about where you are struggling and why you think you are struggling. That's more important. Like, tell me why you think you're struggling. Is it just that you haven't seen enough examples? Or is it that you don't feel like you understand what a permutation is, right? All of that is important to look through, okay? So let's start here. Are there any topics that you think I'm missing? I think I've got everything here. Polynomials as well. Polynomials. There's obviously further calculus. I usually don't find that people are struggling with calculus. Are you guys struggling with calculus? Like, you guys are saying integration's good, so I'm assuming that you can differentiate quite well, all of that kind of stuff. Okay, so let's do this. So again, Tyrese, and then I spelled your name wrong, I'm assuming?
No.
Oh, excellent. And then Lauren, I'm sure I'll get right? Cool. Can we give it a, again, just like we did last time, 1 to 100? Yeah, just do 1 to 100. 100 being I'm fine. Trigonometry, what are we dealing with, Tyrese?
90.
90, cool. Alright. 85 sounds good, so we're not there. Vectors.
95.
95, okay, cool. Alright. 90, so you guys are not losing marks on vectors when you're doing practice. Beautiful. Okay, binomial.
Well, I get the marks for it, but I just don't understand why I'm doing it. Like, if that
Okay.
makes sense.
So are you getting all the marks for binomial?
When there's like the really hard questions, then nah. But like
Okay.
the basic giveaway ones.
All right, well, give it a rank. Oh, there's also probability, like advanced probability. We forgot. So like your Bernoulli stuff, yeah. So put that in there too. Well, what are you dealing with? What do you roughly think? Just give it a number so then we can sort of prioritize it.
69.
69? Of course. Okay, let's go.
Oh, that's 60.
Mm-hmm. Think about your next one so we can do this quickly. I don't want to spend too much of the lesson on this yet. Just gut feeling, yeah? Don't need to be super accurate here. 75, okay, let's keep going.
30.
Okay, so this is the one you struggle with too? Okay, so what are you thinking? 30 as well. Alright, cool. Integration?
95 again.
Lauren? Differentials?
85.
Mm-hmm. Lauren? Keep going, just give me all the numbers quickly, yeah? 100, you never lose marks here? 95, you only sometimes lose marks here? Polys?
87.
Okay, sure. 85, probs?
Maybe 40.
40. 70, so you're okay with that generally? Okay, so let's just add the numbers together. So which one, the obvious one to do at the beginning is perms and coms. Okay, that's cool. That's the one I make it the easiest, so that's good. So you're lucky. Like that's a good one to be struggling with. The next one looks like probability to me. So we're losing a lot of marks there. The next one looks like binomial, which to be honest is just perms and coms. So if you know perms and coms well, you'll know binomial really well. I think let's start there, shall we? So let's just start with perms and coms. Now, I'm gonna, again, just like I do complex like very differently, binomial I do very, very differently. Or even perms and coms, you can be like, oh shit, this is like not what I saw or what I expected. So it should, however, make it much easier for you. But if you're saying that you want more questions, let's do it with a question focus, shall we? So let's go here, and I'll just get a whole bunch of perms and coms problems. How does that sound? And then we're going to do it, but I'm going to first start by teaching you the very highest order stuff. Now, perms and coms historically, is one of the topics where I change the way I teach it the most often, but I think I've settled on a way now that I very rarely get a student being like, I don't get 100% anymore. It's very rare that like my students don't pretty much get full marks every time. So there's a specific thing that I changed, and I'm just going to go through that with you, okay? So I'm going to just put a lot of combinatorics in there, and I'm going to just set the difficulty to 4, and I'm just going to start there, okay? So I'm going to just pop out a bunch of exams. But before I do, I want to tell you what a permutation is. Now, how familiar are you with set theory? Let's start here. Okay, so that's where we're going to start. Okay, so we're going to start set theory. We're going to start with set theory because I promise you, if you understand set theory, then permutations and combinations becomes trivial, like bloody easy, okay? So let's start here. So set theory is the idea of the study of sets. So a set is just a bubble with a bunch of things inside of it, okay? So for example, the set A, B, 5, 6, triangle, whatever, right? So let's call this set capital S. So the set capital S has the things A, B, S, 6, triangle in it. Is that cool? So that's a set, no problems, right? We also talk about the cardinality of the set, which is just going to be the size of the set. How many things are in the set? 5. So the cardinality of this set is 5. Fair enough? You all cool with that? Then the other thing we can do, so you're probably familiar with like the AND or the OR operator, yeah? So for example, like I'll show you something simple. You guys all studied proofs, right? So one of the things, I think I showed you last week, but I might not have, I'm not sure. Suppose we have two sets. Suppose we have a universal set like this, then I've got some item A, and then I've got some item B, all right? So this means A for AND, this means OR, okay? We cool with that? So let's say this. If I was to say A or B, not, yeah? What is that the same thing as? Let's try to think about this. A or B, not A or B, yeah? So let's duplicate this and then we'll get to it. A or B, let's try to re-express that in a different way. A or B is this whole set, yeah? Anything that's either an A, like if you live in, let's say Australia or Brazil, right? Let's say all the people that have Australian citizenship and Brazilian citizenship, okay? This is all the people with Australian citizenship only. These are, sorry, Australian only. This is Brazilian only, sorry. And this is Australian and Brazilian. We all clear with that? So not A or B means that you don't have either Australian or Brazilian citizenship. Are you both clear about that? Okay, I promise you this will link to perms and coms very heavily. I know it doesn't feel like it at first, but I promise you it will. So I know it seems like I'm talking about something completely random, but I promise you it will link very, very well, and it will make everything much easier for you. So,
Sorry.
what was that? Oh, okay, cool. That's okay. How you doing, brother? No pauses. Okay, so not A or B. Let's think about this, right? How could we express not A or B in a different way? So there's this idea here, and I'm gonna prove it to you, and you just get this completely from set theory. This is A, not A. What does not A look like? What does not A look like? Well, that's going to be all of this. You all agree with that? Yep. So this is not A, and then not B is going to be all of this one. This is not B. You got it? You cool with that? That's not A. That's not B. So how do we combine these together to make the left side? Think about it. We're trying to get all of this, yeah? So what we could do you agree that, so if I did not A and not B, can you see that that's the same thing as not A or not B? Do you all see that? Right? So this is like one theorem, for example, you can prove. This is called De Morgan's theorem. Right? This is something usually that we get you to prove in the proof topic. You guys have probably seen already, right? So you can kind of see that one of the things you can do, you can turn or into an and vice versa, and then you can distribute the not signs to the individual things. Do you all sort of see that? So you got and or, and the last one is without. Without. Do you follow that? So for example, if I did A without B, that's going to be just this bit over here, the little crescent bit. This is A without B. Everyone's on the same page there? Yeah? All right, so those are that's a very basic introduction to set theory. The one I really care about, though, is this thing called the Cartesian product. Cartesian product. Now, the Cartesian product is usually denoted times. It's the product of two sets. So let's say I've got a set over here, A, B, C, and 1, 2. I recommend you write down as much of this as you can because you'll get it a lot better if you do. So if you do A, B, C, and I do cross 1, 2, 3. So what the Cartesian product does, and this is the most important thing for permutations and combinations, if you understand the Cartesian product, you will understand perms and coms very well, okay? The Cartesian product just takes all the elements in the set and turns them into coordinates, okay? So let's say that I call this set S, and I call this set, or let's call them letters and numbers, right? This is the letter set, this is the number set. Everyone clear with that? So what I'm going to do is I'm going to make all the coordinates, if I do letters times numbers, right? It's going to make a new set that's going to have coordinates with letters first, then numbers second. So for example, what would the first one, give me one item in the set, just for example. A1. A bracket 1. So you notice it turns it into a coordinate. You'll follow what happens there? How many things do you think will be in the letter times number set? How many things are in there? 6, right? So you go A1, B1, C1, and then A2, B2, C2. You all agree with that? Is numbers times letters the same thing as letters times numbers? No, because the coordinates are backwards. You all see that? So the coordinates are each backwards, so therefore they're not the same thing, right? Then if you were to multiply a set by itself, let's think about numbers times numbers, right? That would be the same thing we, abuse the notation and write it as numbers squared. What would be in that set? Tell me, what would it be? 1, 1, 1, 2, 2, 1, and 2, 2. We're all on the same page? So this is the idea. So what's the size of n squared? Yeah, so it's 4. So notice it's just the size of n squared. That makes sense? So for example, if you had 6 elements in the set, it would just be 6 squared. By the way, this is, you understand that the real numbers are actually a set as well, right? The real numbers are actually a set of numbers. So for example, 1, square root 2, pi is in there, negative 5 on 8 is in there, etc. What do you think the real numbers multiplied by the real numbers would be, by that logic? Give me one element in the set. Just give me one example. Pi. Sounds good to me. What about 1 root 2? Then in that set? Yeah. What about I2? No, that's not in that set. That's outside. That's out here. You all see that? So this is the idea. This is, again, r times r. What would we call that? That's going to be called r squared. Oh, look at that. You know how you said something's in r squared? That's why we keep writing r squared all the time. Do you all see that? So, when people write like, this number is an r squared? That's what they're talking about. It's a Cartesian product, okay? Do you all follow what a Cartesian product is? It's a very simple idea, right? So if you don't understand this, like, good luck understanding permutations, because permutations, let's tell you what a permutation is now. A permutation is a function, and this is actually really, now, if you study permutations properly, they will completely be talking in terms of set theory the whole time. I just gave you a primer to set theory. Do you feel like you'll understand it? All simple enough. Set theory is something you should be teaching to kids, but for some dumb reason, our education system sucks, so we don't teach this to kids, which is really stupid. You've been talking about coordinates your whole life, but you've never really known what the hell they are. So they're just Cartesian products of two sets, okay? Because now, when you're talking about permutations, you're talking about longer coordinates. So what is a permutation then? Let's think about this. So for example, the permutation, k at a time, is a function that turns sets into coordinates of length k. Length k, where no element is repeated. Where no element is repeated. So let's think about this. Let's suppose we had a set S. Let's call it the set S. And inside the set S, let's put the letters A, B, C. You all call that? Let's put D in there as well. Why not, right? Now the permutation, let's say permutations of length 2. Let's think about this, right? Permutation of length 2 is a function that takes a set in as the input. By the way, are you guys familiar with functions that take sets in as inputs? Can you think of any other function that takes a set in as an input? You've seen one in your studies. Very important one. No ideas? Probability? Probability takes a set in as an input, takes an event space in as an input, yeah? Which is a set of all possible outcomes, yeah? So it takes it takes that in and gives you a number out as the output. You all see that? Well, the permutation set is a bit different. It actually gives you something that looks a little bit like a Cartesian product. It takes the whole set in as the input and gives you a new set out as the output. So let me show you what's in the new set. For example, you're going to have all pairs of length 2, right? So all tuples of length 2. So for example, AB, fair enough, would be in there. AC would be in there. AD would be in there. BC would be in there. Yeah. BD would be in there. And then CD would be in there. Yep. What else have you got?
BA.
Yep, so then you can take all of these and reverse them, yeah? Agreed? Fuck it. I'll write them backwards. It's just going to be quicker. BA, CA, DA. How many CB? DB, and DC. Okay, this is really annoying generating it this way, so we need to come up with a better way, right? So we need to come up with a bit of a smarter way to generate this. But this set has a name here, so it's going to be P2 applied to the set S. Fair enough? So this new set is called P2 applied to the set S. Now, if you have to think about it, right, this is always going to be, do you know what a subset is, by the way? Everyone knows what a subset is? So you kind of have learnt about sets, but, you know, not enough of a big deal has been made about it, so you're kind of a bit vague on all the ideas, right? But a subset is obviously a set inside of another set, right? And can you see that P2 is just inside the set S squared? Can you all agree with that? Like, if I was to draw the set S squared, or S times S, like we said, this would include AA in there, yes? But AA would not be a permutation. Why not? Because it doesn't follow that rule of, like, nothing can be repeated, right? AA is not allowed, BB is not allowed, CC is not allowed, DD is not allowed. Yep, because all of those require something to be repeated. Do you all follow? Whereas all the other ones don't. Now, let's think about the size of S squared. What would the size of S squared be? Let's think about this. There's 4 elements in S, so what would the size of S squared be?
16.
Yeah, so the length of S squared is 16. Everyone agrees with that? So, okay, by that logic, if there's 4 repeated ones, what's the size of P2 going to be? 12. That's good, right? P2 of S is going to be 12. The size of P2 of S is going to be 12. Are you all on the same page with me there? That's cool, isn't it? So now, is that what lines up with your understanding of what? Now, here, let's define this, right? NPK, this notation, you've seen this NPK thing before, right? NPK just means the size of P2 at a time, or PK at a time, of the set S. Do you all see that? That's what NPK is by definition. So this is the definition of what NPK has always been. It's just telling you, if you were to write out the whole set, how many elements are in that set? That's what NPK is by definition. Is that cool? So then now what we want to do is, now first understand this, that if I were to swap this A, B, C for dog, fish, cat, and frog, right? Or let's say apple, banana, carrot, D? Surely there's a D. Dill. Okay, apple, banana, carrot, dill. Whatever, right? Is there no fruit that starts with D? Dragon fruit, sure. Apple, banana, carrot's not really a fruit either. So, C? Fruit with a C. Anyway, apple, banana, carrot, dragon fruit. Yes? Do you agree that this would still look exactly the same? It's only, instead of an A, I'm now going to have apples, bananas, etc. So it's still going to look the same, and the sizes are going to be the same. So the set S is kind of immaterial. And this is one of the most important things to understand. So when I give you problems, I'll be like, oh, students are in a group or whatever. Doesn't matter. Can you map it to numbers? If you can map it to numbers or letters or anything, then you can just solve the problem with letters. And then it doesn't matter because the answer is going to be the same. The size of the set is not going to depend on the things inside the set. The things inside the set have no effect on the size of the set. Do you see that? And that's one of the most important insights that you need to make pros and cons easy for yourself. Do you see that? So the key idea here is that what's in the set doesn't matter, right? What's in the set doesn't matter. So that's why I'll kind of always gravitate back to just using letters, because they're bloody easy. Do you all kind of see that? So anytime I have a problem like, okay, John, Bethany, whatever, are in a group or anything, I'm just always going to map it back to a set S, where I have a bunch of letters or numbers in there, and then it's dead simple to solve the problem almost every time, as you're going to see when we get to actual problems here. Are you guys all on the same page as me here? Okay, so NPK is the size of PK with the set S. Now, easy way to calculate this. Let's think about it logically here. Let's see this. So if I was to just draw out all the items in the Cartesian product, what I kind of want to do is I want to imagine that I started off with an empty tuple. This is another very important insight that you need to have, right? I can fill the spots in that tuple any way I want. It does not actually matter what order I fill the items in the tuple. And this is very important to understand, as it will not change the size of the tuple when you're doing a permutation. This is one of the key insights that we use to solve all problems, right? Is that the order you fill the thing in doesn't matter. Okay? So what I mean by that is, like, if you wanted to, I could leave the first one empty and then put an A in the second slot, right? Leave that, put a B in the next slot, leave that, put a C in the next slot, leave that, put a D in the next slot. Do you all see that? So there are 4 possibilities for the first slot because I have 4 things in the set. Do you all get that? Now let's just choose one at random. Let's suppose that we chose B. Yeah? If we chose B, then what have we got? We've got 3 more possibilities. I could put an A in the first slot. I could put a C in the first slot. Right, CB. And, oh, you know what, let me be really stupid about this and just write out all the possibilities, shall I? So, could put an A in the first, I could put an A, B, BB, CB, DB, right? And then what I'm going to do is I'm going to prune anything with repeats because I'm not allowed to repeat anything, yeah? So let's think about this. If for each one of these 4, I'm going to have 4, that would mean that I would have 16 in total. But because I'm going to prune one, I'm going to say, no, but this one's not allowed because it doesn't follow the rules, right? Then what do I expect to have? I'm going to expect to have 3 in the next line, 1, right? So therefore the formula for NPK is just going to be, well, let's say for P2, right? That's just going to be 4 times 3, which is what you guys hopefully already realize. Fair enough? Any problems with that? Cool. So if that's going to be the case, let me pick easy problems to begin with, actually, because I won't pick hard ones, and that's a bit stupid. Let's start with easy ones, and then I just want to sort of show you how to do it the different way. Okay. Let's do this very quickly. Just getting some questions. All right. So numbers one. Okay, copy. This is a good one. All right, so this is a pretty standard problem, right? So I'm just going to try to drop in as many problems as I can here, right? So, in how many ways can the letters? Oh, what the hell? In how many ways can the letters of the word deduced be arranged? Okay. Now let's think about this for a moment. Again, it's a set. And this is where I'm going to sort of start to show you one. There's one more thing I'll show you before I attack this problem. So every time there's a concept I need to cover, I'm going to sort of cover it before I show you the problem, okay? So one of the other things you can do when doing a permutation is that there's also the idea that elements in a set can be considered equivalent under the permutation, okay? So elements can be considered equivalents, right? Now, so let's say that I had a set, so I got A, B, C, D, right? But let's say that I had a set A, B, A, C, D, right? Let's suppose that I had that set for a moment, and then I'm going to label this one A1 and A2, just so that we're very, very clear about it. A1 and A2 are different elements in the set. Okay, they're very, very clearly different elements in the set. To give you an example of where this might happen, suppose that these are like bags of money in a pot, right? Suppose this bag had $50 in it. This one had 10, this one had 50, this one had 100, and this one had 1,000. Fair enough? Because both of these bags have $50 in them, they're considered equivalent as far as the permutation is concerned. So suppose I have 3 people, person 1, person 2, person 3. This person's going to get the first bag, second bag, third bag, yeah? Whether I have A1 here or A2 here, it doesn't matter because this first person still walks away with $50. So as far as the permutation is concerned, yes, those two are equivalent. These two are equivalent to each other. Are we all on the same page? Okay? So they're considered equivalent for the permutation, but they're not the same element. You understand that? So that's going to be the case if I ask you what's P3 this time. So the permutation has the idea that all the A's are equivalent, right? What's the new set? Let's think about this. How are we going to grow this set? This is interesting. How are we going to do that? So I have two A's this time. We have to be a bit clever about the way we do this. I want permutations of length 3. How are we going to do this? When you think about it in terms of set theory, it actually becomes pretty obvious. We have to just think about it the right way. So now you have repeated elements where the elements are the same as each other. What do you do? So give me your thoughts, and then we'll work through it together. Any ideas? So like, I'll give you a hint though. One hint is when we dealt with this set, notice that we have this idea of you've got a whole set. One of the most important techniques you need to learn is to partition the set into smaller pieces. You kind of get that? It's always a good idea to draw boxes around the set and make it into smaller sets that are easier to solve for yourself. Is that fair? So if you wanted to solve this and figure out how many permutations of length 3 there are, how do we solve that problem? Give me your sort of best idea. Because this is initially it seems like a hard problem, but you find that it's actually not super hard. So you understand what I'm saying? So there are 5 envelopes. So pretend this was a question. There are 5 envelopes, right, containing different amounts of money, but these 2 envelopes both have $50 in them. So there are 5 envelopes. I can easily form a question around this, right? So there are 5 envelopes with amount $50. So there are 2 or I can write it like a question, right? 2 M's of $50, and then one with 80, 20, and 70 respectively. If if 3 people choose envelope, you can think of these as like the Chinese red envelopes, you know those? You know those ones, right? So if 3 people choose these envelopes, how many permutations are there? Right? These, how many perms? You sort of see how I construct questions around this? Right? So how many perms? How do you figure this out? This is considered a very hard question, by the way. It's one of the hardest questions I can actually ask you, and I'm doing it right off the bat. How do we do it? What do you think? Do you have any thoughts at all, or not, or none at all? None at all? Just completely stuck? All right, let's start. When you're stuck with a problem, let's just start by listing a few. How about that? Give me one possible permutation. This is why, this is why this is such a powerful technique. So list a few permutations. Give me some examples.
A1 BC.
A1 BC, that's good. A1 BC. Yep. Now, is A2 BC going to be in the set? No, because A2 BC would be considered the same thing as A1 BC. So this does not show up in the set. Does that make some sense? So the first thing I'm going to realize is that when I have repeated elements, I'm going to be smart about this, and I'm going to say they always need to be sorted. That makes sense? So I'm always going to pick from 1 to etc. Right? So if I'm going to have an A1 in there, it needs to. If I'm going to have an A2 in there, they need to be in increasing order, going from the lowest number. Do you all sort of see that? So what other ones are in the set? Give me some more. BCD, cool. BCD. Lauren, give me one. Give me one that's a bit different to those two. A1CD. A1CD. Okay. What's the difference between the two you've given me? Why did I put them together and put the other one down? What can you see?
One has no A in it.
Yep. So this one has no A in it. Very good. So notice this is where the power comes in. This one has 0 A's. What about these ones?
They have 1 A.
They have 1 A in them. All right. What else is there?
A1, A2, B.
A1, A2, B. So A2 is not allowed, so I'm going to only have A1, A2, B. Yeah. Cool. And how many of these got? 2 A's. Notice how we solve these problems? Sets, carve them up, easy, right? Do you see how that's easy now? Can you solve that now? Tell me how many are in this subset. This is easy. How many are in this subset? If you choose the letters B, C, D, how many ways can you arrange them? So let me call this subset A1, A2. Can I do that? Are you guys all clear about what I'm doing here? So let's suppose this set is A1, this subset is A0, and this subset is A2. Yeah? So do you all agree that the total number of permutations is going to be the sum of the 3? The sum of the sizes of the 3? Yep. So okay, A0. What's the size of A0? How do we figure that out? Help me out. If you're going to have no A's, what must you have in the set? What must you have in each tuple? BCD. So then the question is, how many permutations of BCD are there? Do you guys know how to do that, or not really? So just like tell me when you're stuck, so I can go into more detail or less detail. Okay, so if I wanted to ask you, what are all the permutations of the word BCD? Yeah. So again, think of it as a tuple with 3 slots in it. Yeah. So what can I put in the first letter? I can either put, and I can fill them in any order. You all agree? It doesn't matter which order. So let's just do the last letter first. Underscore, underscore, B. What else can I do? Underscore, underscore, C. Underscore, underscore, D. All right, cool. Choose one at random. So choose the C. Let's choose that one. Now, what else could I put in the other 2? Well, let's fill the first one. So Lauren, what do I put in the first 2? What do you think? Yeah, I could put B in there. So I could go B underscore C. You agree? And what's the other option? Yep, so D underscore C. And then let's suppose I chose this one. What can this only be? Huh? DBC. Do you all see that? How many permutations are we dealing with? So there was 3 in the first shot. You agree? How many in the second shot? 2, and then 1. So anytime you want to think of how many permutations there are of BCD, that's going to be 3P3. Again, let's think about this number. The top number means how many in the set. In the set. Okay? Or in other words, the size of S. Do you all agree with that? And this. What does the bottom number indicate? The bottom number indicates the length of what? Length of the coordinates. Do you all agree with that? So for example, if I asked you what is 7p4, what does that mean? That means the 7 corresponds to a set of size 7. Do you all agree with that? So it could be a set with elements 1, 2, 3, 4, 5, 6, 7. Do you all agree with that? And then what does the 4 indicate? I'm forming coordinates of length 4. Coordinates of length 4. Length 4. And the way we said we would always do this, 7p4 is always 7 times 6 times 5 times 4. 4 numbers. Do you all get that? 4 numbers, because each tree loses 1, because we prune 1 more leaf than the last time. And 7 is the largest number, so start at 7. Easy peasy, that's easy, isn't it? So that's what 7p4 means. It means 4 numbers. So if I do 11p7, 11p7, what would this be equal to if you were to write it out? So the first branch of the tree has how many branches? 11. And then you go next branch? 10. And then how many of them do you need? 7. So 1, 2, 3, 4, 5, 6, 7. Does that make sense to you? 11p7 is 11 times 10 times 9 times 8 times 7 times 6 times 5. Everyone cool with that? That's what 11p7 is. Now let me show you a trick here, shall I? If I was to go, so notice if you count them, there are 7 numbers here. There's 1, 2, 3, 4, 5, 6, 7. That's by definition what 11p7 is. Can you test this in your calculator to make sure that I'm not lying to you, please? I just want you to really believe this really deep in your soul, so there's no confusion there. So 11p7 gives you what? 200, yeah, sounds good to me. And then if you just multiply all those numbers on the right hand side, did you guys not know this is what 11p7 means?
I knew that part, like the formula part. Like, if you write 11 factorial divided by, like, the rest of it.
Okay, do you know why that, yeah, do you see why that is the case though? Can you see why, did you not teach you prims and comps? Did you learn that with someone else, or?
He did, but I think he went over it very, very quickly.
Ah, okay, cool. Because I'm kind of surprised. Like, I'm like, you weren't there for prims and comps. Okay, but is everything I'm saying making sense to you? Please stop me if it doesn't. I need you to be very honest with me. If you don't get something, you have to tell me, because I can't read your mind. Yeah. So then the right hand side, do you agree that that works fine? Okay, let's talk about that formula you just told me about for a second, right? So 11 factorial. Let's talk about what a factorial is. If I say 15 factorial, that is by definition, 15 factorial is the same thing as 15 items in the set. Take all 15 of them. Do you see that? So try that in your calculator. Try any number, 6 factorial. That should be 6p6. It must be the same thing, because that is by definition what a factorial is. That's the best definition I can give you of a factorial. Do you all get that? Now, let's continue here. If 15 factorial is 15p15, then, okay, do you all agree that 15 factorial is the same thing as 15 times 14 factorial? Yeah? So then by that logic, what's 3 factorial going to be? Give me 3 times 2 factorial. Everyone agrees with that? Then by that logic, what's 1 factorial going to be? 1 times 0 factorial. And that means, wait, 1 factorial is 1. Yes? So 0 factorial is 1. Has to be, right? Because that's the idea. As you go down, can you also say that? Every time you go down, like if you did, let's write down some more here just to make this all very clear to you so no one's very confused. So 4 factorial is 4 times 3 factorial. Yep. If you divide by 4, you get to 3 factorial. And 2 factorial is 2 times 1 factorial. So that's going to be divided by 3. Yep. And this is going to be divided by 2 to get rid of that 2 at the beginning. Cool. So 0 factorial is the same thing as 1. So 1 is equal to 0 factorial just by following the pattern. Right? So did you guys know that one too? Like, that's cool. So that's good. You have to understand that one too. Now, okay, where does that formula that you guys have learned come from? 5, 4, 3, 2, 1. 4, 3, 2, 1. Cool. Oh, you all see that? So then this 4, if you think about it, is just 11 minus 7. Why? Because you have 11 and then you took away 7, which leaves you with the 4. Do you get that? So 4 is 11 minus 7. So therefore 11p7 is just 11 factorial divided by 11 minus 7 factorial. Cool? Or if you like, npk is equal to n factorial or 1n minus k factorial. We cool? So this is cool. I want you to like be very, very clear about all this so that when we're attacking these problems you can do it. Yeah? So everybody cool with this so far? So okay, let's now go back to this problem. I'm asking you, again, we're solving this problem. You have 2 envelopes with $50 in them, and then you have one with 80, one with 20, one with 70. So if 3 people choose these, how many permutations do we have? This is kind of more in line with what you were hoping, like more questions like this. Yeah, cool. So, okay, size of A0, what are we dealing with? How do we figure that out? So now we know with A0 there are no A's in there. Everyone agrees with that? If there are no A's in there, it's B, C, D. How many have we got? 3, not 3, 3 factorial. So the size of A0 must be 3 factorial. All right, let's figure out the next one. A1, it's a little bit harder, but not much harder. How do we deal with A1? Now we know one of them has to be a 1. Yeah? How many are going to be in that set? If there has to be one A, the others could be a B, a C, or a D. You have to be careful with that, all right? Could be a B, a C, or a D. That's a bit harder. Yeah? So let's draw A1 out as a little tree, shall we? Now, we have to be very smart here. We have to be a little bit smart with how we fill the tuple. So the tuple starts off empty, yeah? So we know we need an A in there somewhere. So what's the first and smartest thing we can do? Again, we can fill this tuple any way we like. It doesn't matter. So what's the smartest thing I can do? Yeah, choose where to put the A. Smart? So I can either put the A at the beginning, A underscore underscore, or I could do underscore A underscore, or I could do underscore underscore A. You see? By the way, I'm just like throwing you right in the deep end here. This is like probably the hardest possible problem I can ask you right at the onset. This is actually probably the hardest pros and cons problem I can ask you. Does that make sense? So as long as you're able to understand it, then we're in good water. So if this is going to be the case, then what am I going to do here? Let's suppose I chose this one. Okay, now let's choose to fill the first slot. What can go in the first slot? B, C, or D. Yeah, see that? So you go B, A, can I just start writing them like this because it's lazy? B, C, A underscore, D, A underscore. Yeah? Now let's suppose that we chose this one. What can go in those two? What can go in the last slot? So if I chose D, what can I put in the last slot?
B or C.
B or C. So D, A, B, D, A, C. Okay, so then how many possibilities do I have? Just counting out my tree. You guys seen this tree method before or not? Yeah? Okay, so how many have I got? I've got 3 in the first hit, 3 in the second hit, 2 in the second hit. Yep. This is why I always like to grow out my tree. I always like to grow trees because it's a lot simpler than, trying to think about things. It's like you can't fuck it up. You have to be a bit of a dumbass too. Do you kind of see what I'm saying, right? So again, the rule I'm going to start with is anytime I give you a restriction, do the restriction first. That's going to be always the rule. Restrict first. Because that's going to be the easiest to deal with, right? If you have a restriction of any kind, do the restriction first and then worry about everything else. Do you see where I'm going with that? Okay. So then what have we got here? What's the size of A1 then, by that logic?
3 times 3 times 2.
Which is?
18.
18. Very good. All right, now let's look at A2. Let's grow that one. Grow that last tree. Okay, so if I've got that A2, what am I dealing with? What's the size of A2 here? How do we deal with that? So let's think about this one. What are we going to need to do? The easiest way I could do this one, you can grow the tree any way you want. It doesn't matter, so let's just try to be a bit clever about the way we do it. So what would the easiest possible thing be to do?
Start with A1.
Yeah, start with A1. So the easiest possible thing to do is actually to pick a slot to place the other letters in. Do you see that? So to pick a slot. But honestly, let's just be really dumb about it. Really brute force here. Let's just pick a slot for A1. Shall we? Where can it go? How many choices do I have?
Start with N.
Yeah. So I can do A1 underscore underscore. Yep. Underscore A1 underscore. Yep. And then underscore underscore A1. Yes. Suppose I then choose this one. What's going to happen then? right? So what am I going to do now? Now I've got to put a slot for A2, yes? So what can I have? I can have either A2, A1 underscore, A underscore, A1, A2. But, there's a but here. What's the but? Think, friends, think. One of these is bad. Why? Because it said when you have multiple, they have to be. All right, we'll ignore it for a moment. I'll see if you can figure it out on your own. So choose one at random. Let's choose that one. What can go in here? What can go in here? So suppose we choose A2, A1. What's the last slot going to have to be? A2, A1B, A2, A1C, A2, A1D. Do you all agree with that? Now there's a bit of a problem here because somewhere else in the tree, do you all agree that somewhere else in the tree there must also be A1, A2B? Do you agree that if I was to grow out this one, somewhere out there, there must be A1, A2B? So what's the problem? Yeah, there's a repetition. So I've actually overcounted every possibility by a factor of 2. Do you all see that? If I grow it this way. So this way, I've overcounted by a factor of 2. Do you all see that? Overcount by 2. That's okay though, because I could just divide the answer by 2. So the answer is like, so I'm showing you this is what I would call the dumb way, the very brute force way. But it would just be 3 times 2 times 3. Do you all agree with that? Divided by 2. So it's 3 times 2 times 3, which is going to be the same thing as? 9. So that's going to be the answer. Okay, so how many of them are there going to be? 3 factorial plus 18 plus 9. Right, so the size of A, the size of P3, right? Let's call it set P3 of S, is going to be what? 3 factorial plus 18 plus 9. What's that equal to? 6? 33, I believe, right? Any problems with this? Got it? It's pretty cool though, right? Like it's nifty. But I want to see, is there a smarter way for me to have done this? Because that was annoying, right? That especially was a little bit annoying. I don't want to be dealing with crap like that. So this is where you have to think of ways that don't create duplicates. This is what you want to do. You want to think of, when you're thinking of ways of growing your tree, try to grow your tree in a way that won't cause a duplicate. Do you follow? All right. So what I'm going to do actually instead is I'm going to choose a spot to put the other letters and then fill the other 2 with A's. That's going to be a lot easier, right? So let's try it again, but we'll try to do it a bit more clever. Let's think of the spot where you don't have an A. So which spot doesn't have an A? You can either choose to put a non-A here, yeah? You can either choose to put a non-A here, or you can choose to put a non-A here. You kind of see that? Just a more clever way to grow the tree, yeah? What that immediately means is that the other 2 are filled with A's. Yeah, just A's. A1, A2, sure? So the other 2 must be filled with A's, and you can order them A1, A2, always, right? A1, A2, A1, A2. That avoids the problem of accidentally getting the A2 and A1 backwards. And then what do? Let's choose that one, for example. What would the options be?
A1B, A2, A1C, A2, A1D, A2.
Do you agree? And what's the size of this set? 3 in the first, 3 in the second. 3 times 3, that gives you, hey, the 9. You see that? So just, you need to think of ways, so the rule here is find ways to grow the tree to grow without duplicates. Without duplicates. So that's actually the main trick that you need to learn when you're doing prims and comps. Do you all see that? Now let's see if this is actually the right answer. So one of the things I can do is I can be like, write some code to generate all permutations of length 3, write some Python code, good idea, write some Python code to generate all permutations of length 3 of A, B, C, D. Cool? That's effectively that's the problem. And this is one of the hardest permutation problems I can give you. I could say you're taking subsets of the entire thing and also dealing with the case that there might be repetitions in there. That's, could be really, really annoying. Okay, sure, that's fine. Who cares? So I'm going to go to Safari. So I'm going to just paste the code I got from ChatGPT here. into this. So there you go. I've just pasted that in. So this is the code that just came out of ChatGPT. Boom, boom. And then click run. And then it will spit them all out for me. There you go. Let's count them, shall we? Oh, but I'm not bothered doing that. So I'm going to print the length of results. 33. Fucking earth. That's cool, right? So, and they're all there. You can look at them all there. But that's cool, right? That's a much easier way to solve these really, really hard problems. You just think of them as sets and you're just trying to count how many things are in the set. I think you can see why that would be easier, right? So it's just, you're just trying to figure out how many things go in that set. You really can't screw this up. That's why, you know, when I told you, like, pretty much most of my kids will get a 95 or plus in this is why. They're just sizing out sets. Now, this problem is actually a very common problem because this one is the same problem, isn't it? It's exactly the same problem. How many ways can the letters of the word deduced be arranged? Now, this one is actually a little bit easier, though, because you're using all the letters. You're not using a subset. So now, let's try to see if there's a simplification we can make. So what if we use all the letters? What if we use all letters? Okay, so I'm going to take the exact same problem we had over here and just see, does it simplify my life at all if I'm going to use all the letters, right? So I'm going to copy this. I'm going to click copy. And then I'm going to go back here and we're going to solve the same problem, but this time rather than using some of the letters, let's use all of the letters. So this would no longer be P3. This is now P. P what? It's no longer P3. We're not doing permutations of length 3. We're now doing what?
7.
Well, I don't have 7 things in my set. How many things are in my set? So in my original set, what's the set I'm shoving into the permutations? What's in the set? Remind me? A1, A2, B, C, D. Why did you say 7? Let me.
Just kind of,
Oh, you're talking about this one.
yeah.
No, I'm talking about this one. Yeah, so we're going to go back to the old problem, solve it in general, and then we'll come and do the specific example, yeah? How? Yeah? 5. Yeah, P5. Very good. So this is going to be P5. Everyone agrees with that? Okay, so now let's think about all the things in the set. And let's try to see if there's a nice way to do this, right? Cool. So just the same way. Do you all agree P5? I'm going to have A1. I'm going to just be a bit lazy here. I'm going to write them A1, A2, B, C, D. And you could just, let's just make a shorthand that if I write A, B, C, that's the same thing as A, B, C. Yep. Are you all cool with that? Just because I'm getting lazy doing that all day. So what now? A1, A2, B, C, D. That's in the set. That's fine. Yeah. Any others you see in the set? Would A2, A1, B, C, D be okay? Why not? Same problem. It's not sorted. Yeah. Can I just make my life a little bit even more hard and just put a A3 in there just because I want to? Just make sure we fully cover everything that could confuse you. So let's do P6. A3, A3. You all get that? So this one is no good. This is in there, so we're going to cross it out. Why? Why is this one bad? Because it's not sorted, right? Not sorted. The A's are not sorted. The A's have to be increasing order. So it has to be A1, A2, A3. Can't be in any other way. Fair enough? Because then that's going to cross out all duplicates that I don't want to see. All right, cool. And then so I could have A1, B, C, A2, D, A3. Are you all happy with that? Yep. And then there's going to be a whole bunch of others, and I want to ask how many of them are there. Well, okay, let's think about it first we're going to be a bit dumb here, and let's choose a specific one, and I'm going to ask the question, what would P6 be if I didn't care that I double counted? So let's say ignoring double counts, right? So let me call that P dash 6, that's going to ignore the double counts. What would P dash 6 of that set be? What would the size of it be? How many of them would there be if I treated A1, A2, A3 as distinct under the permutation? What would that be? How many possible tuples of length 6 are there in this case? What's the answer always going to be? Yeah, 6 factorial. Do you all agree with that? That's pretty straightforward. But then here's the important thing. I've double counted. So let's pick a specific example. So specifically, let's choose A1, A2, B, C, D, A3, right? And I want to ask the question, how many times am I going to see that reappear in my set? How many repetitions of this would I see? Right? Do you all agree, for example, A2, A1, B, C, D, A3 is the same thing and it would have gotten crossed out? And then also A3, A1, B, C, D, A2 would have also been crossed out. How many repetitions are there?
3 factorial.
Why?
You lock B,
Yeah, exactly. There are three things, three repeats. So there are actually six, right? There are six. Um, let's call this set the repeated set. Fair enough. So a repeat of this particular permutation. So the size of the repeat set is going to be 6. So we've overcounted by a factor of 6 is the point that I'm trying to make to you. Do you all get that? So therefore, the actual size of P6 of the set is going to be 6 factorial divided by 3 factorial because I see 3 A's, right? 3 A's. But can I actually be a little bit dumb here and also say, okay, yes, there's 3 A's, but what if we made our life a little tiny bit harder? One more time. Last complication here is that what if I had, okay, now I'm going to do A1, A2, A3, but then I'm going to go B1, B2, and then I'm going to go C, D. Yeah? What's going to happen this time? What's going to happen on this occasion? Well, this time, same thing. I've got a P. This is going to be P7 this time. Yep. Let's take a very specific example. A1, A2, A3, B1, C, D, B2. Fair enough? How many double counts of this one am I going to have? How many possible double counts of this one am I going to have? You have to be a bit careful here, right?
3 factorial times 2 factorial.
Exactly, because there are 3 for the A's, so 3 factorial double counts here, and then 2 factorial for the B's. 2 factorial for the B's. Do you all get that? So therefore, I'm going to have to divide by 7. So P7 of S is going to be what? It's actually going to be 7 factorial over 3 factorial, 2 factorial, and then C, and let's even include the C and the D. There's only 1 factorial for the C, and then 1 factorial for the D. Are you guys all good with that? Cool. So I'm going to come up with a new notation here. This is going to be a bit of a dumb notation, but you're going to see why it's super useful. I'm going to rewrite this as 7, yeah? And then I'm going to list all the unique elements in there, and tell me how many of them there are. So 7, 3, 2, 1, 1. I'm going to write that like that. Is that cool? 7, 3, 2, 1, 1. So what I mean is that's going to mean 3 A's, 2 B's, 1 D, C, and then 1 D. Do you all agree with that? Do you all agree that that is even going to be the same thing as 7, 1, 3, 2, 1? Do you agree that those would be the same? Or not? Lauren, you don't get it? You get it? Because you understand that what I'm doing here, this is the 3, 2, 1, 1. Those are just the same factorials, just in a different order. Order of multiplication doesn't matter. So whether I'm repeating the B's or repeating the A's is exactly the same. Do you all see that? It doesn't matter. It doesn't matter which one I'm repeating. The order of the things in that bracket don't matter. Are you all on the same page as me? Cool. Now let's solve this problem. now we're good to solve this problem. How do we solve this problem? It's easy as hell from here. What do we do? So this is going to be 7 factorial divided by?
3 factorial.
Now what are all the unique letters? You got D, E, U, C, that's it, right? So how many repeated D's do we see?
3.
So you're going to do 3 factorial for the D. E, how many E's do we see? U's, 1 factorial, and then C, 1. Hey, look, it's actually, that's a coincidence, isn't it? I did that on purpose. do you see that? So this problem and this problem are exactly the same. Do you see? So if you can just map this problem back to that problem, then you're gold. You're done. Can you all see that? So this is exactly the same thing. Now I want to point something else out to you here. There's a joke. It's about. Have I told you guys the math joke? It's not a very good joke. Do you ever remember me telling you the not very good math joke that's super important? Okay, so the way mathematicians do things is very, very important that you understand this. So there's a joke. I want to tell you a joke. It's not funny at all, but it's important to understand, right? So the joke goes, a mathematician, a physicist, and a biologist were going to be tested on the way they think, okay? So in the first test, they were all asked to boil some water, okay? So they walked into the room. The physicist saw that there was, a tap and a kettle. So they filled the kettle, pours the water. No problem, walks out. The biologist walks in, same thing, sees the tap, sees the kettle, fills the kettle, boils it, walks out. Then the mathematician goes in, does exactly the same thing. No problem. Test 2, it's a little bit different. So the physicist walks in, sees that this time the kettle's already full of water, so he doesn't have to fill it with water. So what does the physicist do? He looks at it, he goes, should be alright, slaps it on, turns on the water, no problem. Right? Says it's still gonna get hot, no problem. Biologist walks in, thinks about it because he's a biologist. He goes, oh, I don't know what's wrong with the water, but I'm going to boil it anyway. I'm going to kill all the bacteria anyway. Who cares? So he just slaps on the water, gets out of there. Fair enough? Mathematician walks in, looks carefully, grabs the kettle, pours out the water, walks out of the room. Doesn't boil the water, doesn't do anything. Fair enough? He just pours the water out, walks out of the room. And they're like, hey, why'd you do that? What the hell's wrong with you, right? And the mathematician said, well, I just reduced the problem to a problem that I'd already solved before. Do you get the idea? First problem, he walked in, the kettle was empty. So as soon as he pours out the water, problem's already solved. Do you kind of see that? So that's the way mathematicians are supposed to think. What you're supposed to do is like you get this problem, you're like, oh, I don't know how to solve this problem. As long as you can convert it back to a problem you have already solved, you've actually already got the solution to this other problem. Or another way to put it to you is suppose that you've got a problem that you don't know how to solve. So this is a hard problem. Okay? So, and it's like there's like a big canyon, a big river for you to swim over to get the solution. Okay, that's, you're not bothered, swimming over this river and getting to the other side. Too much effort. So what you're going to do is you're going to convert to an easy problem. Okay? And then you're going to solve the easy problem, but it's a transformed solution. And then you're going to undo the transformation. Instead of convert, I should say transform. You know what I'm saying? Transform. And then you're going to undo transformation. Do you guys understand that? So let me give you an example. For example, if I gave you a really ugly trigonometry problem, you're like, I don't want to solve that. What do? T method. Transform it to an algebra problem. Algebra is much easier to solve than trigonometry, right? You could sit there and doing all the trig identities, screw that, convert it to an algebra problem. Algebra is much easier to solve. Solve the algebra problem, now you have a transformed solution, so you have an algebraic version, then undo the T method, and now you've got the actual solution. Do you all see that? All the time. Okay, so suppose you wanted to find the volume of something. Oh, hard, I don't know how the hell to do that. I mean, geometry, disgusting, right? I want to find the volume of a cone. Ugh, gross. Convert it into an integral. Bloody easy to solve. Transform solution, that's okay. Turn it back. You got the answer. You now know the volume in centimeters squared. Do you all see the idea? Or I got a hard integral to solve. I don't know how to solve it. Substitution. Oh, now I have an easy integral to solve. Solve it. I'm done. This is actually maths in a nutshell. I don't know if you realize this, and sometimes as you do higher maths, the ravine gets longer and you just transform and transform and transform and transform. That's kind of the whole ethos of mathematics. That's mathematics in a nutshell. Is you take a hard problem, convert it to an easier problem, and then you're solved. Is that fair? That's why I often spend a lot of time just solving general problems like this. Because once we solve the general problems, as soon as you recognize that this problem is the same as this problem, you're done. Can you kind of see that? And that's what you need to learn as a student. So then the question I would ask is, how many general problems are there in Prems and Comms? It's actually pretty easy. So how many general problems do we need to know? How many problems can they possibly ask you? And you're going to be surprised that the answer is not as big as you think. How many possible questions can they ask you? Possible questions are there. So if you just memorized all the solutions to all the possible questions, then you would know how to solve all the questions as long as you knew how to transform them. Right? That's cool. So how many possible questions are there? Let's think about it. So what are all the tricks that they like to play in the questions that you've seen and done so far? What are all the tricks that they like to play? So sometimes they use like repeated letters, right? They like to do repeated letters. So we're going to use permutations to solve all possible permutation problems. It's pretty funny if you think about it, because you can either have repeated letters or no repeated letters. Is that fair? Another thing they like to play on you is they like to group things. Does that make sense? They like to put things in groups sometimes. Yep. So that's another one. Any others that you've seen when you've been doing the problems? They might put things in circles, right? Any others that you've seen? And then the last one, which is actually the hardest one, is taking subpermutations. Subpermutations. Basically, the idea of rather than, so you have 7 things in the set, rather than taking P7. See, if I take P7, that's an easy problem to solve. But if I take P3, when you have 5 things in the set, that's much harder. It's actually taking subpermutations where 3 is less than 5. That's much harder to solve than if you just took all of them. Do you kind of see that? That's why we have to use all of the set theory tools. Okay, cool. So then how many problems are there? Those are the only complications they ever use. So how many problems are there? They're all binary, on or off. How many possible questions are there? 2 to the 4. Right? 2, there's on, off, 4 of them. So 16 possible types of problems. Most of which are very easy. So for example, if I wanted to, I could have repeated letters in groups around circles where I want you to take a subpermutation of all the total elements. So I could have 10 students that you want to put around a table of size 7, right? So if I want to give you the hardest possible problem, I'm going to turn all of these switches on at the same time. Do you all kind of see that? So I'm going to have 10 students around around a table with 7 chairs in it, okay? And it's going to be a circle, okay? And I want them grouped so that like 3 of the students are together. Fair enough? And also, by the way, 2 of the students are twins, so it doesn't matter where they sit. Do you kind of see that? That's the hardest possible problem I could give you. So as the more of these toggles I switch on, the harder the problem becomes. But the cool thing is once you solve the problem once, as long as you can turn it back into the original problem, you're golden. No problems. Do you all see that? Okay, so that's all we're trying to say. So let's look at a whole bunch more. Now this is where I'm going to get really fun here. We're gonna play another one. Let's try this because this one's going to be crazy. Give me the coefficients. This seems like an unrelated problem, but let's do this. Give me the coefficients of x to the power of 7 in x plus 5 to the power of 24. No, let's not do that. Let's do x to the 5 in the x plus 5 to the power of 7. Let's do that for a moment, shall we? We all cool with that? So again, same thing. I'm gonna solve a more general problem. This is my favorite trick. I always like to solve the more general problem. So what's the more general problem look like? What's the more general problem gonna look like? It's gonna be solving just a plus b to the power of 5, isn't it? Everyone agree with that? I'm just gonna solve a plus b to the power of 5. Yeah? And I'm gonna ask for the coefficient of what? I want the coefficients of x to the 5, so what am I gonna look for?
It was to the power of 5.
Oh, sorry, 7 I mean. Thanks for pointing that out. So what's the thing I want the coefficient of? It's a huh? So I want the coefficient of a to the power of?
5.
Yep, and b to the power of? 2. Everyone agrees? So I just want the number in front of that. And then there are other terms and I don't give a shit about those. You see that? So whenever you're given a problem, solve the more general problem and I promise you it'll make the original problem trivial. Right? And in fact you'll find most of the time the more general problem is easier to solve than the original one. That's the funny thing, right? Most of the time actually, the more general problem is easier to solve than the original one. Now let's think about this. Now, I've got 5 letters. Now here, what's the problem I'm effectively solving? Let's convert it into a problem we've already solved, shall we? Isn't it the same thing as A, B, B? Yes? Now let's think about this for a second, right? If I was to just expand a plus b cubed, that's just a plus b, a plus b, a plus b. So let's expand out all the brackets. A is going to be one of the terms. A. One of the next term is going to be AAB. The next term is going to be BAA. The next term is going to be ABA. Notice how I'm being a little bit cheeky and not expanding them. What other terms do I have? ABB. Any others? BAB. Any others? BBA. And then also, one last one, BBB. Those are all the possibilities, yeah? Now we can group them, can't we? These ones go together. This is actually the exact same problem of, now notice that, what's the coefficient of this going to be? Yeah, why? Because there are 3 ways to reorder AAB. Oh, that's clever. You see that? So why is the coefficient 3? The coefficient is 3 because there are 3 ways to rewrite the string AAB. That's exactly the problem we just solved, wasn't it? So that's a cubed plus there are 3 ways to rewrite AAB. Yeah, plus 3 ways to rewrite ABB. Plus 1 way to write b cubed. So this is the same thing as a cubed plus 3a squared b plus 3ab squared plus b cubed. Solve problems by converting them to other problems. That's always what you want to do, okay? So then, okay, let's look at this one. This is dead simple. a5, b2. We already know how to solve this, don't we? This is equal to, there are how many letters in there? 7. And then 5 repeats of the a, 2 repeats of the b. Which, by the way, we said was the same thing as 7 to 5. Which we said was the same thing as 7 factorial over 2 factorial. Which, by the way, if you look carefully, is the same thing as a combination. That's what a combination is. A combination is just when you only have 2 letters. That's it. You all see that? Combination, 7, 5. So this tells you why 7... Now, sometimes we're lazy and we kind of leave off the second number when we know there are only 2 of them in there. So we sometimes instead will just write this, well, not sometimes, we always write as 7, 5, which is the same thing as 7, 2. Look at that. All this insight that you get. Do you all see that? It's all the same, all right? So this is a combination. Cool. So you know we've already solved this problem. The problem, and if you wanted to solve it again, you just think, okay, well there are 7 things. Grow a tree of 7, then 6, then 5, then 4. Realize I've double counted the a's by a factor of 5 factorial. Double counted the b's by a factor of 2 factorial. Do you all see that? So we just leave off the second number because we don't really need it, because we can always find the second number by just subtracting this number from this number. Do you all see that? So then in general, if that was the case, if I did n choose r, that would just be n factorial divided by r factorial, and then the other number would just be n minus r factorial, which is the combination formula. Do you all kind of see that? And by the way, if you look carefully, this is just a permutation. You all see that? And then you, so basically NCR is just NPR divided by R factorial. You see? All these things that just sort of pop out if you just solve the more general problem. You just have to solve it properly, like you have to actually really solve it. Is that cool? So then, by the way, why is this true? Why is NCR the same thing as NPR divided by R factorial? Can anyone give me a good justification there? It's actually pretty easy if you think about it. What is R factorial? So let's suppose we want NCR. Let's look at a specific example. NCR is the same thing as, let's say, 7 choose 3. Yep. 7 choose 3. Well, let's think about 7 pick 3 for a moment. What is that the same thing as? This is 7 times 6 times 5. You all agree with that? 7 times 6 times 5. Which, again, is the same thing as having, you have 7 things and you're picking 3 from them. Yep? So you have 7, you're picking 3. So if you have the letters A, B, C, D, E, F, G, that's 7 things. Yeah? All right, cool. So what am I going to do? I've got 1, 2, 3, 4, 5, 6, 7. So that there's going to be, if I grew a tree, there's going to be 7, then 6, then 5. You all get that? 7, then 6, then 5. But then what if we think of it a little bit differently and think about it, okay, what if instead we said, is this letter included or not? Let's think of it in a different way and just sort of black them out or not black them out. Does that make sense? So in other words, you've got the 7, this is the set S. We're getting a little bit more abstract for a moment, but I want you to really see the connection between these two, right? So if this is the set S and these are all the things, let's suppose that we wanted to think about, okay, am I keeping the A or am I keeping the B or am I keeping the C or not, right? So what I can do is, let's think of it this way. Let's go 7, pick 3. And then, so I've got, let me write out the letters. A, B, C, D, E, F, G. Those are the 7 letters. And then I want to pick 3 of them. Yeah? I want to pick 3 of the letters. What am I going to do? Right? So I'm going to go, okay, well, let's say the first one I have 7 choices. The second one I have 6 choices. And the third one I have 5 choices. Yeah? But we know we want them to be ordered. Do you get that? So it's going to be 7 times 6 times 5 divided by how many reorderings of A, C, F are there? Right? ACF. Remember how we said combinations, or let me sort of convert this into again an easier problem you're probably more familiar with. Can I just name them A1, A2, A3, A4, A5, A6, A7? Yeah. So how many reorderings of now? So of the 7, I've only picked 3 of them to include in my thing. So I've chosen A1, A3, A6. Fair enough. But we said we only want the ordered one. A3, A1, A6 is not allowed. So how many overcounts have I got? 3 factorial. So I divide by 3 factorial. Yeah? So what's this number at the top? This is going to be 7p4 divided by 3 factorial. It's the same thing as 7c4. Oh, cool. Very clever. See that? So that's how they're related to each other. Can you all see? So again, now we've solved the very general problem. This is now going to be trivial. Can we just write out the answer? X to the 5, and according to our thing, the coefficient should be, well, if I wrote out the term x plus 5 to the power of 7 should just be, well, we're going to have a bunch of terms, I don't care about them, but I know that if I have 5 x's, how many 7s do I have to have? Well, if I had 5 a's, how many b's do I have to have? 2. So I have to have 2 7s. Yeah. So this is, huh? Oh, sorry, 5. My bad. Sorry, I'm a bit dyslexic. You may have noticed by now. Okay, so is that cool? X5, 5, 2. Yep. And then what's the number in front of it going to be? It's just going to be NCR. N being 7. This one being 5. Does that make some sense? If I wanted to, by the way, I could also write 7, 2. That's the same thing. 7, 5 and 7, 2 are the same because by definition that is the 7 factorial broken up into 5 A's and 2 B's, which is the same thing as 2 A's and 5 B's. There's no difference. Again, remember that was the whole idea, is that which letter you choose does not matter. The letter order does not matter. We cool with this? Are you finding any of this complicated? It's all easy? Okay. Now we actually have almost everything we need to solve pretty much every problem in rapid fire now. So let's go ahead. So this is a pigeonhole. I'm not going to do the pigeonholes just yet. I'll leave them for now. I just want to do this. So let's go. Let's do these problems. So these are common problems that come up all the time. So let's do that. So we just want to think which one of these can we turn them into, and then it becomes very easy to solve the problem, right? Like we said. So here's a common one. There you go. Committee of 6 is chosen from 7 boys and 8 girls. How many different committees can be formed if there are no restrictions? Well, tell me. Now, this is where, again, think of it as a set. Okay, think of it as a set. Let's call it B1, B2, B3, B4, B5, B6, B7, and then 8 girls. Girl 1, girl 2, girl 3, girl 4, girl 5, girl 6, girl 7, girl 8. I'm not going to usually do this, but I'm just doing it the first few times just to make sure that you guys understand everything. So if there are no restrictions and you're choosing 6 of them, you're putting it into the P what? P6 set, right? But it's a committee, so it's not saying that the places of the students matter at all, right? So basically we want ordered. It needs to be ordered. We actually don't care, you know, where they show up. We just need to, of these people, we just need to pick some of them, right? So you're gonna do the P6, but then you have to understand that it needs to be ordered. Is that cool? So in the sense that both alphabetically and numerically. Fair enough. So all the B's come first and all the G's come after that. Fair enough. So if I was to do it this way, then like for example, committee of length 6.
Yo.
Hey, what's up?
Busy.
All right, just give me a sec. Sorry, I just need to give him something.
Oh shit, you told me to.
Nah, it's all good. Alright, good luck. Sorry, I'll catch you soon though. See you, bro. Sorry. So length 6, yeah? So let's pick any one of them. B1, B5, G1, G4, G6, G7. You all happy with that? Yep. But again, the same one, B1, B1, G1, G4, B5, G6, G7, that would not be in the set. You get that? Because it's not ordered. So not ordered. Got it? That's how you're thinking about this. Okay, so if this is going to be the case then, what do we do? How do we solve it? I mean, if there are no restrictions, how do we deal with the fact that they're in the wrong order potentially? Yeah. Oh, hey, Summer, what's up? You can come and sit in. Do you usually come to class at the same time as these guys?
Yeah.
Okay, yeah, just come sit in. That's fine. Mum should be there soon.
Just go find your
Yeah, just find my mum. It's fine. All right, so you'll follow what I'm doing here. So how would we solve this problem? Can you help me out? Let's see. I want to see how far you guys can take everything we've said today. So there are no restrictions. What do we do?
There's 15 of them.
There's 15 of them. Agreed.
Pick 6 of them.
Yeah, you just want to choose any 6 of them, and then you want to guarantee that it's going to be ordered. So then you're just going to divide by all the repeats, right? So in that case, that's going to be the same thing as. Well, you're going to do okay. There are going to be how many? You said how many were there again? 15 of them, and then you're going to pick 6 of them. Is that fair enough? But then you're also going to divide by the fact that those 6 can then be reordered any way you want. So 6 factorial, which is the same thing as we know as 15 C6. Do you get that? So in other words, if you want to take a tuple and then just remove out all the scramblings of them, just divide by 6 factorial, which is the same thing as choose. So 15 C6 is the same thing as that. Okay? So that's going to be the first one. That's easy peasy. All right, the committee must have 4 boys and 2 girls. It's even easier. 4 boys and 2 girls. Well, what do you do then? Grow the list, right? 1, 2, 3, 4, 5. So first off, you do take, now let me show you a quick way to draw the tree, because we don't want to like be sitting there drawing it all the time. So what I do is I just draw 3 and then I say how many there are in it, right? So I'm going to say, okay, there's going to be 8 in the first because there are, sorry, 7 in the first because there are boys, right? So let's just pick one. I just like to write one example all the time. So suppose we pick B2, right? And then the others are 1, 2, 3, 4, 5, 6. Yeah? And then same thing. 6 choices for the boy. Yeah? So the committee has 4 boys and 2 girls. So there's going to be B2, B3. I know it has to be sorted though, right? I know it has to be sorted. So that's going to be the idea there. B2, B3. 1, 2, 3, 4, 5, 6. Yeah? And then there's going to be 5 boys to pick in the next slot. Yeah? So it's going to be B2, B2, B3, B4. And then, right, 4 for the next slot. B, what do we got? B7, right? B2, B3, B4, B7, right? But then also realize here that if you just did 7 times 6 times 5 times 4, that they can be in any order. Do you kind of see that? They could just be in any order. So how do I deal with the fact that they're out of order? I divide by the 4 factorial. Okay, that's the repeats of the b, like we said before. Got it? So that's kind of how we're going to sort of think about this. Or another way, again, turn this into an easier problem. There's going to be a bunch of boys and a bunch of girls. There are 7 boys. So how many total do we have? So of the boys, there are going to be 7 factorial boys. That's going to be the tree of the 7, of the boys. So you have the boys tree. There's going to be 7 factorial of them. And ask how many times is every one repeated? Or let's say sorry, of the 7 boys, you want to pick 4 of them, yeah? That's what we want. So 7, pick 4, yeah? But then they're all repeated a bunch of times because all 7 of them are there. So you're going to divide by, right, 7p4 divided by 7 factorial. Fair enough? 7p4 divided by 4 factorial. 7 factorial. You see that? Or in other words, you said that's the same thing as 7c4. So if you know you want things to be ordered, just use 7c4 instead of 7p4. Cool? That's the thing you want to learn. So for the boys tree, you go 7c4, 7, choose 4, and then choose a particular example for the girls tree. So how many girls do you got? Well, you got 8 girls, and you want to choose 2 of them to fill the rest of the committee. You all cool with that? And that's going to give you all the possibilities. 7c4, 8 choose 2. So that's going to be the answer. 7c4, 8c2. Cool? Now, there must be a majority of boys. Okay, now, this is where you really want to get into set theory, right? You really want to think about the set theory ideas. So this is all the possible numbers. This is the full set of combinations, ordered combinations. You guys, like, I can speak a bit more abstractly, or do you want me to like write a few examples? Am I losing any of you, or do you get the idea here? Okay, so for example, if I know that there is a majority of boys, we'll ask, okay, how many boys could there be? There are 6 people in the committee, yeah? So there could be either 0 boys in the committee, 1 boy in the committee, 2 boys in the committee, 3 boys in the committee, 4 boys in the committee, 5 boys in the committee, or 6 boys in the committee. Do you all agree with that? Yep. If there's a majority of boys, how many boys do there have to be? Sorry? 4, 5, or 6. So we're going to include just these guys. Do you all see that? 4, 5, or 6. We know how to find, which one did we find in the last case? 4. So, okay, if that's 4, then how are we going to do? So we know the size of 4b is going to be 7c4, 8c2. What's the size of 5b going to be? What do you reckon? Any ideas?
7 choose 5,
Mm-hmm.
8 choose 1.
Mm-hmm. And then 6 boys?
7 choose 6, 8 choose 0.
Yep, and 8 choose 0, if you think about it, would just be 1, right? Cool? Because why is that? Because it's the same thing as 8p0, right? Divided by 8 factorial. Yep. And 8p0, that's just, what is 8p0? If you're picking 0 things, what does that mean? Well, it's going to be 8 factorial over 8 factorial, isn't it? So, sorry, 8 factorial over 8, isn't it? 8 minus 8. What's 8p0? Put that into your calculator. I believe that should just, is that 1? Oh, sorry, no. Sorry, my bad. It is 8 factorial over 8 factorial, but this last number needs to be 0 factorial. That's, I don't know why I said 8 factorial, because there's 0 places that you're swapping. Cool? So that's cool. So, all right, this is your answer for this one. Do you get that? So you're just going to add them all up, and you're golden. You see that? So if you can just sort of reason about the set itself, it's pretty easy. Tanya will not go on a committee if Tom is on the committee. What do we do there? Now, if Tanya is not on the committee, if Tom is on the committee, again, same thing, set theory, right? Set theory. What's the possibilities? What are all the probabilities here, right? So you have a committee here where you have Tanya and Tom, TNT, right? Now, Tanya, Tom, so Tanya and Tom are both on. Then you got no Tanya and Tom, fair enough. And then you got Tanya and no Tom, and then you got no Tanya and no Tom. You see how freaking useful this is? Bloody easy, right? So okay, we know that, which one are we not interested in? We're not interested in Tanya and Tom both being there, right? So we are interested in all three of these. These are all the three possibilities that we want to count up. So if you just took committees, all the possible committees, how many possible committees are there? It's 15C6. So this whole thing is 15C6. Yeah? But we want a subset of those. So which ones are we interested in? Well, okay, it's pretty easy to work out no Tanya and no Tom. In fact, all of these are pretty easy to work out, aren't they? Right? Because if you know that you don't want, you've got all the people, but you're not including Tanya, well, what would the size of this one be? Let's think about it, right? How many people are there now? If you took Tanya out, or if you took Tom out?
14.
Yep, but you know for a fact that Tom is there. You have to be careful there, right? You know that Tom is there. Fair enough? So what does that do for me?
13.
So there's 14 people. There's still 14 people, right? But then, yes, you've taken out both Tanya and Tom, right? So there's 13, like you said. And how many of them do I need to take? 5, because there's 6 in the committee, and of those 13, I need to pick 5. And then this one is also going to be the same, isn't it? Because why should that be any different? They're symmetrical. And then this one, if I'm not picking Tanya or Tom, what have I got this time?
13G6.
Done. How freaking easy is that, right? You can't really screw this up if you understand what you're doing, right? So that's what you should get. I do believe. Yep, we got the right answer. Beautiful. Cool. 13 choose 5 and 14 choose 6. Oh, but it's saying 14 choose 6. Why 14 choose 6? 13 choose 5 times 2. There's 2 of these, yeah? You agree with that? So this is, hold on, wait. Which one are we doing? I just want to make sure we didn't screw that up. Oh yeah, there's, so total number of committees minus, oh yeah, another way you could have done it, by the way, that's a good point. You could have just taken all the committees and then subtracted this. That actually would have been even easier. Do you all see that? So again, use your set theory ideas. That would have been even easier. So the total number, 15 choose 6, could you just figure out how much that is?
5,005.
Yep, 5,005. And so the even easier, how many of there if you definitely pick Tanya and Tom? So guaranteed to pick Tanya and Tom. Now, there were 16 people, right? So now you have 14, there were 15 people, isn't that right? So now you have 13 people left, and then you're choosing how many of them to fill the committee? 4. 13, choose 4, that's it. Cool? So you can do it either way, but generally speaking, the way that requires less calculation is usually going to be less error prone, because you could have screwed up on any one of these, yeah? So you just got to be a little bit careful. Can we see that the other one is the same though? Can we double check that the other one's the same? So 5,005 and 5 minus 13C4. Let's make sure that we're fully not screwing anything up here, right? So you should get 4,290, I believe. Is that what you get? Do you agree with that? Yeah, cool. And then, so the other way would be 13 choose 6. So if we didn't screw up, which I think we might have, we have to be careful here. Do these, if we add these two up, do you also get 4,290? Oh, you do? Okay, cool. Beautiful. Well, yeah, then set theory works. Should work, right? Why shouldn't it work? Do you all see that? It's okay, let's do as many problems as we can before the others show up. At this point, we're pros. Okay, now this one's fun. This is the one I wanted to solve with you. Disgusting. They haven't taught us this. Okay, what do we do? This is a great question. This is very much a band 6 question. How am I going to solve this? I'm going to generalize always. Solve the more general problem. So what's the more general problem? A plus B plus C to the power of? And what am I interested in? There's a whole bunch of terms here. I don't care what they are. But what I do care about is the term where I get an x to the power of 3. You get that? So an x to the power of 3, if you look at these terms, how can I make an x to the power of 3? There's really only one way. I need to pick an x, and I need to pick an x squared. Yeah? So I need the term b, oops, rainbow, b, c, and then the a would be to the power of 3. Do you see why? And then I just want to know the coefficient of that. Are we all clear? Okay, help me. Can you guys figure it out without my help? So the more general problem, can you know, I just want to make sure that you guys are on top of this. So what are we doing? How do we find that number? What am I, again, remind me step by step. I'm looking for the number of ways I can rearrange this string what? This would be just like before, A, B, C. Do you all agree with that? How many ways can I rearrange that string?
5 factorial.
Yep.
Divided by 3 factorial.
Mm-hmm. 1 factorial, 1 factorial. That's this thing. 5 factorial, 3 factorial, 1 factorial, 1 factorial. Cool? Do you all see how I did that? Anyone confused? No? So then what's the coefficient going to be? Well, a to the power of 3, that's just going to be 1, so you can ignore that. But this number is just going to be 5 factorial over 3 factorial, which is the same thing as 5 times 4, which is the same thing as 20. Cool? Do you see how we do it? So again, this is very much my trick. I'm pretty much one trick pony, guys. Like it's not very hard. But if you learn how to use it, it's incredibly powerful. It really doesn't matter what the problem I give you is. It's all right. Just close the door. So this one over here. Now we want the constant term. Ooh, okay. How are we going to deal with that? It's okay. So to find the constant term, what are we asking for this time? Again, more general, just like before. Always more general, right? So to find a constant term, I want all the x squareds to cross out with the x's. Does that make sense? So I need twice as many x's as I need twice as many of this term as this one. So whatever this value is 2k, and whatever this one is just going to be k. Do you all get that? Yep. So I want the term, again, a plus b to the power of 15. I don't know which term I want, but I want one of them to be k and one of them to be, and b to be 2k, right? But k plus 2k has to add to 15. Yeah? So then k has to be, do you all see what I did there? So k has to be 5. So actually I want the term a to the 5, b to the 10. You didn't really need any algebra there. I mean, could have just used common sense, right? So one could be 5, one could be 10. All right, and then what's the coefficient here? Same thing. So it is
15 factorial divided by 5 factorial 10 factorial.
Yeah, I think you're getting the hang of it, right? So 15 factorial divided by, oh sorry, my screen freezes sometimes. So please unfreeze screen. God damn it, screen. Where the hell did you go? Come on, you bastard. Safari. Okay, give it 1 sec. I don't know why it does this. It's so strange. Just like sometimes goes, nah, screw you. Okay, cool. Can you all see that? So then the answer is, what is it?
For the coefficient.
Mm-hmm.
729,729.
It's funny when they have like funny numbers like that, eh? So then what would you do? You go 729, right? And then you'd multiply that by 3x squared to the power of 5, and then 1 on x to the power of, what is it? 10. I don't need the minus in there because it's an even power, so I can just sack that off. I know that this guy and this guy are going by. And so the answer is just 729. 729 times 3 to the power of 5.
I already did the 3 to the power of 5.
Oh, yeah, that's fine. So the answer is 729, 729. Sure. Cool? You happy with this? Alright, so now I'm going to let you guys pick problems that look hard to you. How does that sound? Okay? I'm going to let you guys pick some problems that look hard to you. So, let's go. So, have a look. Does one look okay? Do it or not? Easy? Too easy? This one's cool because it can show us a bit more set theory stuff. So we can do that. C and L are together in any order. Do you want to do this one? Lauren, how do you feel about this one? Should we try it? Yeah, let's give it a try. It's cool. So same deal. It's always going to be the same, right? We're always going to attack them in the exact same way. So how many arrangements of the word Olympic are possible if C and L are to be together? Well, okay. So what is the word? What are the now you want the full arrangements, right? So you want the full arrangements, but you know that you want the C and the L together. So are there two C's? No. Are there two L's? No. So that's pretty easy. So really, let's make it simpler for ourselves. Let's go grow our tree, shall we? Let's grow our tree. First thing we can do is we want to choose a spot for the C and the L to go together, right? That's what we're going to do. So how many have we got? We've got 1, 2, 3, 4, 5, 6, 7. So there are going to be 7 spots for the first, right? 1, 2, 3, 4, 5, 6, 7. So there are 7 spots for the first. So let's just choose 1, 2, 3, 4, 5, 6, 7. And I'm going to pick this. Yep. I'm going to pick those 2 spots. Fair? So what I'm going to do is I'm going to put the C in the first spot. Yeah? That's going to force the L to go in the second spot. Or I could flip them. Do you get that? So I could also flip them. So once I've picked the spot, I can either choose 1, 2, C, L, 1, 2, 3, 1, 2, L, C, 1, 2, 3. Got it? And then for the rest of the spots, it's damn easy. What do I have to do for the rest of the spots? So I just grow the rest of the tree. I just draw this when I'm doing the rest of the tree. So what's happening for the rest of the tree? So I've got 7 here. I've got 2 here. And then what's the rest of the tree going to look like? How many spots are left? I've got 1, 2, 3, 4, 5, right? So I'm going to have 5 factorial here for the rest of them. But are there any repeats? Any of the letters are repeated? Nope. So it's just 5 factorial. So it's going to be 7 times 2 times 5 factorial. Do you get that? 7 times 2 times 5 factorial. Now how do I simplify that? It's going to be 7 times 2 times 5 factorial. How do which one of the answers is correct then? Oh, sorry, it's not 6. Sorry, it's not 7. We screwed up there. I screwed up. Why did I screw up? It's not 7. We made a mistake. Made a boo-boo. So how many spots are there actually? Look carefully. How many places can I place it? There's 1, there's 2, there's 3, there's 4, there's 5, there's 6. Yeah, careful. Don't screw that up. 6 times 2 times 5 factorial, which is the same thing as?
2 times 6 factorial.
Good. Cool? We happy? So again, these problems aren't really super bad. You just really have to know the techniques, right? So let's keep going. Choose another. Let's just keep going. Oh, we didn't deal with the circles, right? You want to do some circles? let's do a circle. Yep. So I told you those are all the possible problems. So let's solve the problems in general, right? That's what we're doing. So let's do this, shall we? So you have 4 boys and 4 girls. So here they're doing, this is the idea of you have equivalent elements, right? You have equivalent elements, and also, well, are they equivalent? Is it important that there's 4 boys and 4 girls? Yeah, it is, right? They're equivalent. It actually matters where they are. Is that cool? So the boys have to be together. So this is, let's think of how many toggle switches we've got on this one. We've got equivalent elements. Yeah. So let's think about this. We have equivalent. We have circle. Anything else? They're asking us the group as well, right? So this is like a pretty hard question. Can you all see that? This is like we're getting up there in the difficulty. Let's try that. First, let's think about what would happen if I put things in a circular arrangement. Okay, shall I? So let's just think about how many overcounts for a circle. Okay, so let's pretend that I had a random tuple A, B, C, D, E. Okay. And I want to ask the question, how many overcounts are there? Fair enough. How many overcounts are there for this one? How many different ways can I rearrange this so that it forms a circle? So if I made a bracelet out of these, right, I'm going to have A, B, C, D, E arranged like this. Do you all agree? So arranged around a circle, it actually doesn't matter whether I take it from the A or from the B or from the C or from the D or from the E, right? So normally, without any restrictions, there would just be 5 factorial possible arrangements. You all agree? So 5 factorial possible arrangements. Thank God they're not taking subsets of this one, right? So that they're including all the boys and girls in the table, right? If you put subsets on here, this would be pretty much the absolute hardest problem I could ask you. Do you kind of see that? If they went, okay, instead of taking 8, let's take 6. Let's take 6 of the boys or girls. That would be very much a second year university level combinatorics problem. That's a very hard problem and not something I'd expect you to solve. Do you kind of see that? All right, but if that's going to be the case, those are the 3 toggles we have. We already know how to deal with groups. Those are easy. We know how to deal with equivalences now, but we don't know how to deal with circles. But that's okay. We can do that easily. Suppose, let's ask this question. There's 5 factorial of them. Do you all agree then? If I start counting at the B, do you all agree that B, C, D, E, A is the same? Right? If I count C, D, E, A, B, D, E, A, B, C. Yep, those are all the same as far as I'm concerned. E, A, B, C, D. And also A, B, C, D, E. Those are all the same. So I've overcounted by a factor of 5. You all see that? So there are 5 overcounts. So the actual answer is 5 factorial over 5. Do you get that? So you got to divide out the other one. Now, so let's suppose for a moment that you could flip them as well, right? So let's suppose these are people right now. So if you flip the people upside down, their heads will be on the floor. Do you all see that? But that's no good. But if it was a bracelet and they were just like reversible beads, then I could absolutely just mirror it so that it's A, E, D, C, B, like that, right? And that's exactly the same, isn't it? So then A, B, C, D, E is the same thing as A, E, D, C, B. Cool? So then this one gives you an overcount by a factor of 2. So just be aware of that. So it's really 2 possibilities. You have, if it's a circle, you're always going to need to divide by the number of elements, right? So divide by the number of elements. Number of L's, okay? And then if it's flippable, divide by 2. Always 2, because then that's a symmetry. You all see that? Any problems there? Do you get that? Because you're looking at it carefully, so what's the problem?
So if it was a bracelet, which is circle and flippable, would you divide by 5 times 2?
Yes. Yeah, that's right. So you divide by 10. So in this case, it would be 5 factorial over 5 times 2, which is just going to give you, yeah. Cool with that? Happy? All right, then let's attack. All right, so find the number. So a table has 4 boys, 4 girls sitting around it, and the seating is arranged at random. So first, let's just find all the possibilities, and then just divide by the number of people at the table. That's pretty easy, isn't it? Because it's going to capture all the repeats. You see that? So every single one of them will be repeated 5 times. So we're going to do just what we always did and just divide by. We're arranged at random, so we're going to divide by 8 when we're done, whatever the answer is. Okay. So let's do that. So we're going to say number of ways of sitting around the table so that the boys and girls alternate. Okay. So they're going to alternate 1, 2. So boy, girl, boy, girl, boy, girl. So I'm not going to really care about them, like where they are, but it's going to be boy, girl, boy, girl, boy, girl, and then boy, girl, right? So I've got 2, 4, 6, 8. Are you all clear with that? Now, if it was arranged by a circle, we'd arrange it around, but that's okay. So you have 4 boys, 4 girls. What does the tree look like? It's actually pretty easy. What is the tree going to look like? First, we're going to place the boys. How many different places can I put the boys in? So the first boy, how many spots do I have for him?
8.
Yeah, I have 8 spots. Oh, no.
4.
Yeah, there's only 4. Do you see why it's only 4? Because there's let's call this boy 1, 2, 3, 4, 5, 6, 7, 8. Because if they're going to alternate, I can't put them here. I'm not allowed to put them here, 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 or here. Do you get that? So I'm just going to choose to put the boy there. Fair? Now what? Now for the second boy, I can choose to put him wherever I want, right? So I go, same thing, 3 spots. Yep. So boy 1, underscore, I can put boy 4 here. Underscore, 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 underscore. You cool? So it's going to be 4 factorial. Can you all sort of see this whole tree is going to be 4 factorial? So we're going to have 4 factorial in this tree for the boys, yeah? And then for the girls, 4 factorial again, yeah? But I've overcounted by a factor of? 8. So I've overcounted by a factor of 8. So for any one of these, you could rotate the thing by 8 different spots. So you've actually overcounted by a factor of 8. Got it? So you're going to divide by 8. So the answer should just be 4 factorial times 4 factorial divided by 8. Cool? Which is the same thing as 3 factorial squared. You see why? No, that's not true. 4, that's idiot. Sorry, my bad. So 4 times 2, so that's going to be 3 factorial times 4 factorial. Oh, just plug it into the calculator, damn it. What's the answer? 72. 72. So the answer is actually double that for some reason. What do we do wrong? I actually think they got the wrong answer there. 3 factorial times 4 factorial. I think they might have the wrong answer there. I think they've got the wrong answer, but that's okay. So find the number of ways of sitting around the table so that the boys and girls alternate. So the way that people usually attack this is that, okay, by the way, there's another way to think about this. If you've got these 5 factorial people, yeah, you've got these 5 factorial people. What you can do is you can just choose a seat for the first person and then reference all the other people relative to that person. Is that fair? So with the 5 people, you got 1, 2, 3, 4, 5 people, right? So another way you can sort of think about this, if you like, is you can choose a seat for the first person. So where can we put the first person? Well, there's going to be 5 spots, right? 1, 2, 3, 4, 5, right? So you just choose one. Yep. Oh, hello. Hello, friend. You're George, right?
Yeah.
Ah, how you going, George?
Where are you?
Yeah, just take a seat. Won't be long. Yeah, just leave it alone. I think other people are coming. Yeah. So what you can do for this one, we'll continue with this next week. Do you guys want to spend more time on prims and cons? I'm assuming, so we'll do more on next. Did you find this generally helpful, or yeah, find it okay now? Not freaking out. So then, what I want you to do is by next week, do lots of practice. Bring me more questions, so then we can go through them. You know what I'm saying? So go through here and then just slap them on there, and then we'll do them. But anyway, let's attack this one quickly. So what you can also think of it as if I placed the first person, doesn't matter where I put them. Like say I placed the A person, let's say here, right? In the 3rd spot. You will be able to scan down. There will be one place where the A is in the 3rd spot. Do you get that? So if you just place one person and then you do everything else relative to them. Hello. No, let's see. It was not your Lauren. So you're. Oh wow! It begins. No, Chanel, right? Yes, got it. Okay. Was Christian joining in person? I don't remember. Oh, is he joining online? Does he always join online? Okay. But yeah, do you sort of see? I'll very quickly finish this question with you guys, and then we'll get on to extension 1. So another way you can sort of think about this, which is extension 2, I mean. So another way we could think about this is if you took all of these people. Let's pick. And this is a bit annoying here because you got 4 boys and 4 girls. So let's just call them B1, B2, B3, B4, and then girl 1, girl 2, girl 3, girl 4. Fair enough. Hey Blake, how you doing? So then let's place the first boy wherever the hell we want. So let's pretend that boy 1 was over here. We're gonna leave them there. Fair enough. So then we need to think. Okay, how many places can we place boy 2? Well, boy 2 has to be here, here, or here. You all agree with that? So there's going to be 3 spots for boy 2. 1, 2, 3 spots for boy 2. Yeah. How many spots is boy 3 going to have? Just 2. And then how many spots is boy 4 going to have? Just the 1. And then for the others, obviously, you could just do the whole tree. Then the girls could go in any one of these spots, right? It's going to be 4 factorial of them. So that's pretty straightforward, right? So yeah, in this case, another way to get it would be 3 factorial times 4 factorial. Is that cool? Yep. So our old way, we would have missed half of them because we would have because by placing them in any order and then just dividing by 8, you would have missed. I'm trying to figure out which ones we missed though. Oh, because yeah, okay, that makes sense. Because by doing, is there anyone else is going to come or is that it? Is there any more? How many people are there usually? Is there because I don't know. So there's 5 of you guys, and then Christian and Mariano usually, right? But I don't know if he's coming because he hasn't said anything. So I'll find him later. Okay. But other than this, that's what we get. You got it? I'm not going to do part 2 because I got to go on with extension 2. But for next week, do as many questions as you can. Bring them to me, and I will make you even more boss than you are right now. So that'll be good. Okay. So I'm going to leave this one. I'm going to stop streaming that. I'll send